So thanks for that introduction. As was mentioned, I'm currently chairing a National Academies Committee, but I would also highlight there was a National Academies report that came out on 2022, which is a relatively up-to-date resource on research and development needs in this field, and I'll be touching on some of that as I go along. Just to provide some context, why would we want to do marine carbon dioxide removal? This week is a big week in climate policy. It's the first week of the Conference of the Parties, or COP, down in Brazil. There was a big report that came out of UNEP about the emissions gap. And this is just showing a schematic from a recent review paper where the positive numbers, the black line here is the historical and estimated future emissions of carbon dioxide, primarily from human-driven use of fossil fuels, but also from deforestation. So we've been seeing globally an increase in carbon emissions to roughly about 10 billion tons of carbon per year. And depending on how you make your assumptions about policy implications and commitments and things like that, that number is going to probably remain large for at least the next decade before it starts trending down. Whether it goes up or stabilizes or starting to flatten is an open research question. What's important and where carbon removal might fit in is we really need to get human emissions of carbon dioxide and eventually other greenhouse gases to net zero, where the human emissions would be balanced out by any deliberate human removals. And to stay on the Paris climate 1.5 degree warming scenario, you would need to follow this sort of blue line here, which is a very rapid reduction in emissions, a huge amount of decarbonization shown in purple. But most of the scenario building and models suggest that there's some residual emissions of things that are hard to abate. And to balance that, you need some amount in orange of negative emissions or carbon dioxide removal. What's important on here also is to note this estimate of the current ocean sink. There's already a substantial natural sink of carbon dioxide from the atmosphere.
Travel, if you're trying to do it,
If you folks could mute if they're in the audience, thank you. So the ocean already removes about 2.5 billion tons of carbon per year, and any carbon dioxide would be on top of that. So what are some of the approaches? Well, some of them are more geochemical or electrochemical, where you're changing the chemistry of seawater, for example, by adding alkalinity or by electrochemically stripping carbon dioxide out for storage elsewhere. And in both of these cases, you're basically altering the solubility of carbon dioxide in seawater, and these changes would then induce a flow of carbon dioxide through air-sea gas exchange into the ocean. And I put some of the chemistry down below if you're interested. This ocean alkalinity enhancement has gotten a lot of interest lately. And I just want to put that there's an ocean research component, but there's also a techno-economic life cycle analysis, because these approaches for adding alkalinity, whether you're adding minerals or you're just adding dissolved material that has a high alkalinity as a solution, all of that requires a substantial amount of activity on land, mining carbonate rock or silicate rock, grinding it up, processing it, perhaps running it through a chemical reactor to create a solution, transportation of that. And so in terms of thinking about overall net carbon removal, you would need to think about the whole life cycle, not just what happens if you add alkalinity to the ocean. And on the right-hand panel, this is just showing a recent student modeling study from the engineering school here at UVA, where the ocean alkalinity enhancement, at least with the assumptions they're making about cost and technology, really wouldn't come into play versus other removal technologies till late in the century. And that depends a lot on, as I said, cost and technological assumptions. So what might this look like? You know, you're adding alkalinity, and this is just a large eddy simulation showing a very fine scale, like where you have a discharge pipe or a release from a surface vessel. So you're adding alkalinity in the surface ocean. It's being turbulently mixed by the boundary layer. That acts to lower the partial pressure of carbon dioxide. And that's what drives the air-sea gas exchange, is that actual chemical reaction. But air-sea gas exchange for carbon dioxide is actually quite slow. And the equilibration time is on the order of a year. So it matters a lot. What's the fate of this alkalinity? How long is the high alkalinity water stay at the surface? Does it get mixed below the subsurface? Does it get subducted? And how does it get dispersed over time? And that's where a lot of the oceanography comes in, is in terms of monitoring, reporting, and verification, where, for example, on this left-hand panel, a ship might be adding alkalinity. That initial perturbation would then be stretched and stirred and dispersed over time. So you'd need physical measurements to track that tracer dispersion. You'd need chemical measurements to see if by adding alkalinity, do you precipitate other minerals? How do you affect the partial pressure of carbon dioxide right near the surface that drives air-sea CO2 flux? And then you would want to be looking at, are you altering the plankton community? Are you having biological impacts on plankton or fish larvae or invertebrates or things like that? And so on a short time scale of days to weeks, you might do this monitoring through a combination of autonomous assets and ships. But over a longer time, because of dispersion and transport, you're going to need to fold in remote sensing where feasible, and also numerical modeling. The other pathway that people have suggested are more biological approaches. So I'm going to talk more about the open ocean approaches of, for example, growing seaweed and then taking that seaweed up and depositing in the deep sea. So seaweed would need nutrients in the right light environment to grow, probably in a coastal region for logistical reasons. As you grow a lot of seaweed, you're going to remove carbon dioxide from the surface ocean, and that would be replaced again by gas exchange with this long time scale. Or you might add a limiting nutrient in a coastal or open ocean system. Iron is typically talked about because there are large swaths of the ocean that are iron limited, and that we've shown already from scientific experiments that adding iron, creating new biomass that then sinks out of the ocean can alter the carbon dioxide levels in the surface ocean. So let's take a look at this ocean fertilization by, for example, by iron. Now you have, in addition to the complexities of ocean physics and chemistry and air-sea gas exchange, you're now modifying the planktonic ecosystems with potential ramifications for fisheries, which is a potential for a substantial effect on other marine industries. And in many cases, what we've seen is that by adding iron, the goal is not just to increase the amount of, say, phytoplankton, it's to alter the structure of the phytoplankton community. You would like to have more phytoplankton, but also grow larger phytoplankton that lead to a greater amount of export of organic carbon to the deep sea, rather than carbon that's quickly remineralized back into inorganic form. Because it's really only the organic carbon that's export to the deep sea that can be a sequestration, act as a sequestration or storage for some extended period of time. In terms of iron fertilization, I've mentioned that there had been a number of field trials already, though these field trials were done to understand ocean biology, not really carbon dioxide removal. So the left-hand panel here is showing dots of different types of perturbation experiments where different nutrients were added. and it's on top of, the color gives the surface nitrate. So the places that are iron limited are places with a substantial amount of surface nitrate throughout the summer. So for example, the North Pacific subpolar gyre, the equatorial Pacific, and the Southern Ocean. And on the right, I'm just showing some results from some of these experiments. For example, the soiree perturbation. This is a satellite image on the right-hand side showing the phytoplankton bloom that was generated. So you can see the stretching that's happened from the initial much more compact injection site. And then you can see that in terms of chlorophyll, you had a low chlorophyll background that went up by almost a factor of 5 to 6 over the iron addition period, and then stabilized. So you had a large accumulation of phytoplankton while you were adding the iron, and then once that iron addition ceased, you basically stabilized the community. Many of these experiments didn't last long enough to track the fate of this organic carbon and whether it's truly export. And then either of these geochemical or biological approaches is going to, one of the key things that we talk about a lot in this space is additionality, which is, has your intervention, has your perturbation actually increased the net amount of carbon dioxide that's being uptaken from the atmosphere and stored in the ocean? And of course, there's already a lot of carbon that's being cycled through physical chemical processes, through the uptake of anthropogenic carbon dioxide, and through the biological carbon pump of phytoplankton growing and sinking into the ocean. And I'm just showing on here, the black arrows are sort of the pre-industrial, with some pre-industrial estimates. The blue is what's going on because of anthropogenic effects such as climate change and rising atmospheric CO2, and CO2 removal would have to be on top of that. And this makes for a really challenging monitoring and verification. You might be able to monitor and verify small-scale pilot experiments, but at the basin to global scale, we won't be able to see this signal for many decades, and only if carbon dioxide removal is scaled up substantially, because the ocean is already removing such a large amount of carbon from the atmosphere. So I've mostly been talking about some of the geophysical aspects of this, things like efficacy or efficiency, does it work? Additionality, there are, particularly for some of the biological terms, you may be able to stimulate biological productivity in one place, but do you rob another location of nutrients? And so maybe there's an increased flux in one region, but it's not additional overall to the overall ocean uptake. Durability or permanence, how long does this added organic carbon, or for the geochemical techniques, how long would that alkalinity stay in the water column in order to remove carbon dioxide and store it for at least many decades, if not centuries? And the geochemical techniques tend to, at least right now, the expectation is they'd have greater permanence or durability. Geophysical scalability, can you actually scale up? Is there enough coastal region, for example, to grow enough seaweed to have an actual substantial impact on atmospheric carbon dioxide growth? And then, of course, the monitoring, reporting, and verification. Other aspects of this are the environmental feasibility. What's going to happen to fisheries? Will this have negative impacts on other aspects of the blue economy or conservation goals, recovery goals, for example, for protected species, commercial fishing? There are technological issues on scalability. There may be techniques that are geophysically scalable, but the technology, it's not reasonable that they could scale up or how quickly they could scale up because of the massive size of this. We're talking about millions to perhaps 1 billion tons of carbon and carbon dioxide that would need to be removed in order to meet global estimates of these residual emissions that need to be abated. Cost is critical. and different techniques have different cost estimates, and then energy and resource demands, and then social and institutional factors that could be either enhance some techniques or be barriers to other techniques. There was a recent assessment by the High Level Ocean Panel, and I put the link to the report in, that tried to look at some of these different aspects for different techniques. And don't worry about the details of this, but just, some of these techniques, each technique has different limitations and different opportunities. And some of these are knowledge-based, some things we know quite well. So for example, for iron fertilization, we've demonstrated the ability with more than a dozen experiments to add iron to the ocean, track the impacts on plankton, though not necessarily all the carbon dioxide variables you'd want. But we are just starting to look at, for example, material and energy cost requirements to actually do this at scale, or what the environmental impacts might be. And then thinking about paths forward for carbon dioxide removal, and this is again out of this recent high-level panel report. The report looks at principles for responsible and effective marine carbon dioxide removal development and governments. And I would say one of the key things that we're seeing in both the research space from academia or national labs, but also from industry, there's a growing number of startup companies that are moving forward with different technologies. They are starting to do field trials. And I think one of the key findings from the scientific community is that these field trials need to be conducted in a responsible manner. There needs to be a robust assessment of ecosystem impacts. So not just how is it affecting the carbon cycle, but how is it affecting fisheries and plankton ecosystems or coastal ecosystems. We need robust monitoring, reporting, and verification standards, particularly as these approaches might be folded into either a voluntary or a compliance regulatory market, where actors would be paid for altering the ocean and get carbon credits. We would need really strong, robust monitoring, reporting, and verification. Transparency and community engagement. Much of this work is going on in coastal communities, and how will those coastal communities be brought in? Are they only notified after the fact, or as the project's moving forward, or are they actually participants in this process? And then one of my concerns is right now there's no purpose-built governance framework at the international level. So there are bits and pieces of national and international law that deal with permitting and regulations, but nothing is really tailored for marine carbon dioxide removal. And so then I'll stop there and take questions.
Thanks a lot, Scott. So at US CLIVAR, we aim to connect and build communities of academic researchers and elevate priorities among US funding agencies. We see this issue emerging as really important. What can we do? It seems like it crosses lines, private, public. What are some ways that we can be involved to help things and be relevant?
I think, obviously CLIVAR has a lot of expertise on the physical side. There has been a fair bit of work that's been done mostly on the modeling side. So, for example, Seaworthy, which is a nonprofit NGO, has been developing modeling tools. And, one of the things I'd like to see is, you don't want bespoke, you don't want industry developing bespoke tools that we don't understand. And so I think one of the things that can really help is we're going to need physical models across different scales, from the sort of the deployment scale, so very sub-mesoscale models of plume dispersion, boundary layer mixing. You're going to need sort of sub-mesoscale, mesoscale models to track those There was an interesting field program this summer in the Gulf of Maine, and that group out of Woods Hole and other institutions been doing a lot of modeling. And then bringing in the observations. What's the right observing approach, right? Not everything can be instrumented to the hilt. So how can we optimize observing strategies to basically inform the modeling, but also inform the permitting decisions? Because models will be used a lot as we develop regulations and permitting for understanding, how big these perturbations will be, what their environmental impacts might be.
So just to put a finer point, so are you saying that we should try to make sure that the state-of-the-art models remain in the public domain? I'm just trying to think of how you push back.
And state-of-the-art models and the state-of-the-art observing systems. I mean, in an ideal world, I'd like to see the modeling and the observations be transparent. Obviously, industry needs to do what they need to do for their development and working in with their investors and things like that. But I think it's important for the federal agencies and for academia to be involved and to play the role as a disinterested, well-informed observers who can, basically evaluate claims that are being made by industrial groups.
Thanks.
And you mentioned federal agencies. Certainly, right now, that's a little chaotic. NOAA was at one point moving forward in this space. DOE through ARPA-E was moving forward in this space, but I honestly don't. I don't know if there are any. I can't see all the. I don't know how many if there are any feds on the screen. We're trying to engage and help the agencies because there are regulatory agencies like EPA and Army Corps that need to make decisions, and we need to help them and DOE, NOAA, NSF to the extent that it wants to play this role.
Great. Up next is Lily.
Yeah, thank you very much, Scott, for a great presentation. And just jumping off of, I think, Dan's question here, which we talked a bit about the public-private partnership aspect of this, but I think there's a third, well, there's probably many stakeholders here, but the third that comes to mind for me is communities, and you touched on this, like coastal communities being kind of test beds for this work. And I'm curious if you are aware of if there are currently best practices in terms of how do we go about doing effective engagement on this topic, or is that literature that the field needs to lean into more deeply?
I mean, there is a growing, so that high-level panel report touches on a little bit. National Academy report touches on a little bit. There is a social science and norms and practices that are being developed both for coastal communities and also in many parts of the world. This will be in indigenous groups as well. So there are some, sort of best practices. The Aspen Institute tried to put together a code of conduct. I'm forgetting. Somebody else has a code of conduct. None of these have been widely adopted, but people are kind of trying to move forward. Without promoting Woods Hole, it used to be my home. I mean, I think they did a pretty good job of pre-engaging and engaging honestly with some of the fishing communities and some of the coastal communities. This is one topic, when they do these social science surveys, there is very little awareness of these topics, even among coastal communities that are closely tied to the blue economy. And so some of this is raising awareness in a way that, is basically, can you get to having social license for doing this in a practical way, but also in an ethical and genuine way? You don't want to make promises. There will be some things that will happen, and whether they've actually been caused by the CDR pilot project or not might be very difficult to figure out.
Thank you. I appreciate that.
All right. Up next, we have Ka.
That was great, Scott. Thanks for the informative presentation. I do want to echo that community engagement. I'm involved in the Loch Ness Ocean Alkalinity Enhancement Project out of Oxford. The public engagement was part of a big component of that project.
Right.
This new business, people do have to reach out to the local communities.
And I think they worked, my memory is that they worked with EDF that has
That's right.
experience in this area.
Yeah. So that just want to echo that is one important component. But my question may be more general. One challenge I see, Scott, here is, as you mentioned, startup companies are coming into this space rapidly. And actually, the first carbon credit has been issued to Planetary through Isometric not long ago. But then there's scientific research, which is slow in its nature. So the challenge I see here
Are you looking at my desktop and you can see I'm behind on all my tasks? Research is slow.
Well, yeah, happy to hear what you have to say. But for example, the carbon credit issuing process is not necessarily done in a traditional like a peer reviewed fashion, right? It is more. I have seen the report. To me, there are some uncertainties that they could improve, but then that's the challenge. They want to move forward. They want to move forward quickly, and then I'm just worried that the MRV process is slow in its nature. And how do we? What do you think? How do we handle this challenge, mismatching pace?
I mean, one thing I would recommend, because this is, we're all learning, right? Most of us were trained as physical or biological scientists. We don't have backgrounds in politics or economics or regulatory. There have been there was a nice review paper, not on marine carbon dioxide removal, but more broadly on carbon crediting and some of the challenges that have shown up in terrestrial systems. So there have been some nice review papers on that recently. And there are a lot of built-in systemic issues. For example, the registries, you have registries, you have verifiers. They're often paid by the industrial group, so there's sort of this built-in conflict of interest. There are, parts of the scientific community are trying to push for truly independent third-party verifiers. But the only way for that to happen would really be if they're funded by some non-industry group, whether it's a foundation or whether it's a national government. For compliance markets as well, there's equally a lot of problems with verifying efficacy, verifying additionality. I think this is where efforts like Seaworthy, where they're producing tools that are, they're not being produced by an industry group, they're being produced, externally to that, and trying to have codes of conduct and transparency. I mean, I think one of the really important things here is, yes, Planetary got carbon credits. This is for their experiment in Halifax Harbor. They, without a lot of venture capital investment, they need that selling some of the carbon credits to support their research and development. And I appreciate the bind they're in. I think maybe less important than the fact that they actually sold the carbon credits is the degree to which their data is transparent. And they're actually, I think, doing a pretty good job. They're working with researchers at Dalhousie and other academic communities. And so I really do think this transparency, maybe we go back later on if the data is available and we find that, well, maybe we shouldn't have credited that. I'm more worried about, models and standards getting locked in. So we'll need flexibility that maybe the standards for what gets credited right now might not be what's credited in a decade. We might have stricter standards for how we do the intervention and how we do the monitoring, reporting, and verification. Does that help?
Oh yeah, yeah. Thanks for that.
All right, up next is Natasha.
Yes, thank you, Scott.
Hi,
Thank you for
Natasha.
the talk. Hi. And thank you for organizing this effort at a higher level early enough, so we have the opportunity to provide the feedback, you know, when it still matters. I have several comments. I mean, any kind of climate intervention will have to be at a larger scale in order to
Right.
achieve the numbers that you are proposing, and there is a lot of there are a lot of gaps of knowledge, as you mentioned. For example, with regards to ocean, there are studies which are showing it depends even on the depth that you are doing some of these
Oh, very much so, yeah.
experiments. So this is, I agree entirely that we need to engage a broad scale of models, from starting from the smaller scales, because these are smaller scale processes, but then going all the way high up to the global scale, the climate scale, where we see now the effect that we will have in the climate. Because yes, it might work. Yes, it might not be intrusive to the biogeochemical system, although I don't know how it is going to happen, but it might not, it not only might not be useful for climate, reversing climate trends, but also it might be introducing tipping points, or it might be introducing other adverse effects in climate, in the broader climate, not just
Right.
the. So we do need interdisciplinary studies. And there are already models now in CDR-MIP, which I think it was a part of CMIP-6 and is going to be further on, hopefully part of CMIP-7. There are large-scale models engaged in this through experiments like CDR-MIP. But these are different experiments, the way they are designed, than what you are talking about right now. So my question is, how do you think that this is going to play? How we should be engaging to get this organized, such as, you know, we bridge the gap between the information we have from these larger scale models to what we are asking here? Thank you.
Yeah, so, you know, and I, you know, part of my past research was, you know, running basin scale, global scale models. And it's, you know, people have been running iron fertilization experiments for a couple of decades, or, you know, there have been ocean alkalinity experiments in those models. They're in some sense pretty idealized. You don't worry about how any of the processes of how this happens. You don't worry about anything at the subgrid scale. You just sort of add a tracer. In many cases, there were no environmental feedbacks. So I do think there needs to be this, you know, I mean, I sound like I'm on a soapbox. You know, it's basically a hierarchy of models with both in time-space scales, but also perhaps in biological complexity. And then the other axis is we need to be engaging with the integrated assessment modeling community and the, you know, the life cycle and techno-economic assessment modeling community. A lot of that comes out of the engineering space rather than the geophysical space, because the assumptions that, you know, the policymakers unfortunately are not going to be looking at CMIP-6 or CMIP-7. You know, the staff of the delegates going to things like COP and putting together their nationally determined contributions at best might get some summary out of, you know, an integrated assessment model. And so we need to be making sure that findings about efficacy or permanence, you know, things that, you know, I think, you know, David Ho and others have been talking for quite a bit about the fact that, you know, the air-sea gas exchange for carbon dioxide just has a long time scale. It's longer than other gases because of acid-base chemistry. And that's sort of a, you know, standard, you know, first semester chemical oceanography problem set question. But the ramifications are really big, because even if you modify the ocean, you know, if it takes a year or 2 years before the carbon's actually removed, that parcel's moved a long distance away, it's stretched, it's been dispersed. you can't, it's not like some of the other carbon removal where you could actually go to a specific field site and do a longitudinal study over time. The Loch Ness example is great. After like a couple of weeks, they couldn't detect that the dye tracer is basically dispersed. You've got the complexities of the Gulf of Maine with its biological physical cycles. And so, yeah, I do think we need to be, it can't continue to be idealized Earth system models, even though I love Earth system modeling. It's got to be more practical. We've got to fold in models that have data assimilation for the actual eddy structure around these pilot experiments. For example, you can't just use an eddy resolving model because you'd actually want to track what actually happened, not what happened in a statistical sense. I would say that there have been some good studies on the modeling. Katja Fennell's written a couple of good articles. There have been other people who've thought about some of these modeling constraints in much more detail than I can get into in this short talk.
Yeah, thank you.
All right, I'm gonna recognize we have gone over our typical time, but in the sake of discussion, I think we should keep answering some questions. So Arena, I see your hands up. I can't hear you, Arena. No, I see you're unmuted, but I can't hear. So maybe play around with your audio settings. For the sake of time, I'm going to put you one down in the queue. I'll remember your name. Victor, go ahead.
Hi, thanks for the talk. You guys can hear me, right?
Yep, I can hear you fine.
Okay, cool. Yeah, so I'm an undergraduate student at UNC. I'm planning on going to like graduate school to like study like ocean modeling and also like get into the aspects of like MCDR and sort of like what research questions we can answer behind that. I obviously like know like a lot of startups are getting into like, sort of like deploying field trials, testing out the waters, so to say, which is both like very like groundbreaking, but also like kind of scary at the same time because a lot of the research questions like are still yet to be discovered, and when you propose to like dump alkalinity or like other projects, there is that like sort of risk to carry on. My question more comes on like sort of like the social side. I know like for like the general person, the way to like sort of like reduce like CO2 emissions is like like sort of finding ways to reduce your own carbon footprint. And there's obviously a very human aspect of that where like any person, like it doesn't have to be a scientist, can sort of find ways to do that. But when it comes to like these sorts of projects with like MCDR and like creating these facilities and building all these different things, the human aspect is like kind of like it's a lot more disconnected compared to like finding your own way to contribute to to fixing the problem. So I was just wondering like what are like your sorts of like thoughts on like the future of like MCDR when it comes to like interacting with like actual people and like the general public as well?
Right. I mean, I would, I apologize if I didn't put this in as a disclaimer at the beginning. I don't know whether we should do marine carbon dioxide removal. I do know that we need to decarbonize our economy. And as you mentioned, there has been a push for people to think about it at the individual level, but it's a systemic issue. It's not just, actions by individuals are not going to fix this problem. This is a multi-governmental level, an economy-wide problem. And so, yeah, marine carbon dioxide removal isn't going to fit into those sort of individual, actions of individuals. It's really going to, I think, either be driven in a small voluntary market by corporations, and you can argue whether that's good or bad. Corporations buying credits to offset their emissions, there are positives and negatives of that, or more of a compliance market where, for example, the EU, has talked about various, aspects of carbon emissions limits and how that would fit into a compliance market. I think at the end of the day, there's lots of things that happen in the carbonization space that individuals aren't aware of. But it's just raising broadly the awareness of the need to decarbonize and perhaps deploy some of these carbon dioxide removal, because these are going to be, none of these are free. There aren't any, there are some small co-benefits to some of these techniques, but it's not like you're making a product and, by the way, you also happen to remove some carbon and that's an added co-benefit. Most of these would be new industries that would have to grow up to scale. And as was mentioned, yeah, if they're going to have an impact, people have different cutoffs, but the current emissions are 10 billion tons carbon. So it's, if carbon dioxide removal is, at the million tons, you're 10,000 times smaller than current global emissions. So it's got to be probably more than 1 million tons a year to even have a noticeable economic effect.
Great. So we have Arena's put her question in the chat. She says, Scott, can you tell us a little bit about the recent history of iron fertilization experiments? I know there were a bunch of iron fertilization experiments in the 90s and early 2000s. Then the UN basically prohibited that. Have the iron fertilization experiments restarted, and are they going to continue?
Well, that is a really good question. It's also a complicated one. There were some projects that were moving forward. There was a German national project that was going to move forward. This was more than a decade ago. There was also a private actor who worked with First Nations in Canada that got a lot of bad press because there were a lot of claims being made without a lot of robust scientific measurements to actually support those claims. I would suggest you take a look at either the National Academy or this Ocean Panel report, because it's not just the UN, there are multiple international frameworks where different aspects of carbon dioxide or geoengineering might be managed. So for example, the London Convention and the London Protocol deal with dumping of material in the ocean. And so there's a lot of discussion, is CDR actually dumping? There's, within the London Protocol, there's an amendment to deal with some aspects of research and development. So within that framework, people are trying to formulate ways where responsible research and development can move, or research and development, perhaps not deployment, can move forward at this time. The other big UN treaty that's going to come into force early in 2026 is the Biodiversity Beyond National Jurisdictions, sometimes called BBNJ. So there are things that can happen in exclusive economic zones, but this would be covering the high seas. That's not in any nation's EEZ. And they're just spinning up. But so for example, how would the BBNJ process look at deployment of large amounts of iron to the Southern Ocean in places that's mostly in the high seas? We don't know that yet. So it's a really complicated governance structure. Some of the work that's gone forward is being permitted for example, in the US, Loch Ness received an EPA permit. So there are national regulatory frameworks that are guided by some of these international treaties, but different interpretations by different nations is still an issue. I'd say that just to wrap up on ocean iron fertilization, there's a community of researchers who are quite engaged. There's a group called Axios that has been trying to develop plans and is, big proponents for moving forward on the research and development side. But I haven't seen a lot of energy from funders yet, at least within the US.
Looks like we have okay, we've got the link. Our next question is Mame.
I'll make it quick. So going back to your hierarchies of models, for the ocean, it sounds a bit like weather service for the ocean. If you take all together, right, because you want a hierarchy of nested models at the end, and you want to assimilate them, and you want to forecast where the eddy goes. And when you put stuff in there, you want to know how effective it was, right? So you essentially need all the infrastructure that a global weather forecast system has, but for a larger part of an ocean basin. So
Yeah.
that sounds pretty much like that.
I mean, there is a growing body of ocean forecast models that use, for example, altimetry to, to update, the mesoscale field. But yeah, it's to do this, you really would need, some form of assimilation analysis forecasting that does look a lot like numerical weather prediction.